Somebody else just told me. Yes?
66.
66.
Yeah.
Ooh, that's lucky. Let's see. All right, let me see. Hold on. Sorry. Oh my God, where's this? 67. 66. Here we go. Is this the one about decibels?
I can't remember.
They give you this equation here of 0 over I. Okay. Yeah, okay. So this is, you guys have all heard the word decibels before. I think I mentioned this when we first got into logarithms. So you got like Richter scale, you got decibels. What is decibels? What does it measure?
Loudness of sound.
Say again?
Loudness of sound.
Yeah, how loud sound is relative to some base comparison amount. So that's exactly what these letters here mean. This is the intensity of sound. So I is the intensity of the sound you're interested in. Sound we are hearing. And I0, which is called I naught. I naught. This is the comparison. This is like the baseline amount, which is 10 to the negative 12. Yes? They tell you. Yeah, good. They actually tell you. And this is in, these are not huge importance, but it's watts per square meter. So real quick, guys. I'm not going to suddenly start teaching you physics. But if something emits a sound, it travels out in a circle, like a sphere, right? So something emits a sound, it's going to go out in all directions, correct? So as it moves out, the sound has to cover the inside of this sphere. Let me make sure you understand. So as the sound moves out, it's sort of like creating a sphere. So as it moves more and more out, isn't there a larger area that sound gets kind of distributed across? Just like light. Turn on a light, it has to move out, and of course the closer you are, the brighter it is, because as you move further away from it, the intensity of light has to go cover a bigger area. Does that make sense? That's why these units make sense. Watts is like energy per second per area. So the further you are away from it, the less intense it's going to be. So this is at the source. This is how many watts per square meter it's putting out, right? The sound source. This is what we compare things to. And then they ask us, blah, 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 blah. How many decibels are emitted from a jet plane with a sound intensity of 8.3 times 10 to the second watts per square meter? So I want to figure out the decibels. So all I got to do is plug it in. Is that cool? So it's sort of like, how many times more intense is this to this? I would divide those. And then we take a log just to make it get to a scale that's better for us to talk about. This is exactly, not exactly, but this is roughly how we do Richter scale for earthquakes. So this is really just a plug and chug. And just, are you able to use your calculator? What base is this?
10.
Good. There's not a base indicated, just like a square root doesn't have a little 2 in it, right? So I know this is a base 10. So you just throw this in the calculator. Is that cool? I know there's like a lot of moving parts to this problem that kind of explain a lot at you. This is basically the lowest amount of sound that we can hear, most of us, right? And then I compare that to what the actual sound is that I'm experiencing. I see how many decibels it is. So you've all heard the thing about a rock concert is 100-something decibels and whatever else, and then ear damage happens at this level, and oh my God, don't go to a rock concert. You've all heard this before? No? Or is this old? Okay. Is that right? Okay. Anything? Yeah.
How would you plug that in? Is 8.3 on top?
Yeah, so there'll be 10 log. This is specifically always this.
Okay.
This is the baseline.
So that'd be 10 more, 10 to the power of -1?
Yeah.
Okay.
And on top I got 8.3 times 10 to the second. So you can actually plug, I would just plug it exactly like this. 10 times log of 8.3 times 10 to the second divided by 10 to the negative 12. Yep.
Okay.
Maybe. I said maybe. So that problem sounds difficult. It just ends up being a, can you tell where things go? All right, maybe. So this is just, I mean, every time we learn a new function, it's not a bad idea to see, well, how the hell do we use that function in real life? So this is one application of logarithms in real life. Okay, anything else from homework stuff? Okay. All right. Did everybody get, I think somebody came in, who didn't get updated homework sheet? Did we get that? Oh, you got it. Oh, you got a question? What's up?
It's on 6.7. I just wanted to know if I did it right, because I got a negative number.
6.7?
Yeah. Number 21.
Oh yeah, this is the one I want to say a little bit about. Okay, let me take a look at what this is, and let's see. Okay, oh, okay, so this one's, all right, let me show you guys this one. This one's not even one I really have to talk about. Wow, okay. Ooh, so here, it's sort of like the one we just did. This, let's do this. All right, it doesn't ask you to do it. Real quick, look at 21. How long will it take for the population to reach 900? Well, which variable in here represents population?
The equation?
Yeah, which variable represents population?
P.
Yeah, P. There's only two variables, correct? There's P, which is a function of time, and then there's time. So I want to know how long will it take. So I don't know time, but I do know the population is 900. So I'd put a 900 here and I'd start to solve this. Right, so if the issue is how to solve that, we can talk about problems like that. But something I want to do real quick, let me see. I say real quick, and then it all depends. Let's see. This problem does not say, well, number 17 says graphic. But I'm going to graph this. I really will. The blazing speed, okay. All right, let me pull this over here so I can get the, oh, that's beautiful. Y equals 1,000 divided by, negative 0.6. Okay. So it looks like it's just going straight up, right? If you go out far enough, well, if I put it in there, I did put it in there. Yeah, that's right. It's going to be way there. All right. So so it looks like it's just increasing forever, right? But what makes sense about fish in a pond? Can you can the population just grow forever? Right? At some point, now technically you will never get here, but isn't there a point where the fish shall be taking up every single spot available in the pond? You're not going to get there, correct? It's just like humans are discovering there's a lot of humans on the earth, and basically nature says, wait a minute, let's do some things so we can kind of cut this down. So we got to be careful about population getting too large, because then resources get too scarce, blah, blah, blah. This kind of function here right there. Anything that's in that form is going to have this kind of ceiling. I don't know if you guys are with me. It's going to have, so if I look back at this chart, at this graph, there's a ceiling for the fish. And what's the ceiling look like it is? 1,000. So if I change this top number, it'll change where the ceiling is. So what seems to be this pond's capacity for fish? 1,000. So once they hit 1,000, they don't stop reproducing, but the resources get to a point where they're dying off at about the same rate that they're reproducing. So then it's going to stay at 1,000. Before you get there, there's plenty of resources. Babies are born, not many fish die, everybody's happy, and then you're like, oh shit, right? So it's not, nature isn't this perfect, but it is roughly, can be modeled with this kind of function. Are you guys kind of with me? So population growth, there will always be variables that make it reach a maximum. So how many humans can be on the earth? Well, not an infinite number. So at some point we're going to go, oh shit, right? Okay, maybe, are you guys? So, all right. So did you have to graph this? No. Would I graph almost anything they asked me to do? Shit, yeah. Just to see what's going on, right? So for number 21, you just have to put a 900 right here and then solve for t. Now I say just. You just have to do that, but you guys, in fact, let's just do this homework problem right now. When I say let's, I mean you. You guys just totally missed all that. I'm sorry, whoever's at home. So I know P, are you gonna work green? No. Know this, and I'm curious, how long until it reaches 900 fish? And of course, that's the population. I'm going to put 900 in for P. Right? That is the base level of working with functions. Don't just throw 900 into T, because that's the input. That doesn't make any sense. 900 is not a time, it's a number of fish. So it's population. Now, does that look like a nice equation to solve? Is that the equation you hope I would give you? Anybody have an opinion on that? Express it, feel free. You can say, shit, no. You can say, please don't. Okay, or, okay, great, everybody likes it. I'm gonna give everybody this kind of stuff, I love it. How do what really sucks about this equation? Can somebody identify what sucks about this equation? Try to solve it.
Variables on the bottom.
Variables on the bottom, right? In fact, it's not only on the bottom, it's in the power of a thing that's on the bottom. Scheisse. So let's take care of one of those problems immediately. How do I get the part that has the variable in it on top?
Multiply them by that.
Yeah. So if I multiply both sides by this, then my variable is at least on top. Right, one of you guys is going to work. Is that cool? I just distribute this. And on this side, of course, I just get 1,000. That looks much better. All right, why am I doing this for you? What would you next? What would have to happen? Where's your variable at? Yeah, it's right there, right? Is it by itself? The piece that has the variable in it? Nope. So I want to get rid of this, correct? Maybe. By the way, some of you guys might notice you could just switch these, but we'll get there. What would you do next then? I'm sorry? Yeah, good. Go ahead. Keep going. Yeah, good. Keep going. I love it. I don't know. Some of you guys think that you're supposed to know ahead of time everything you're going to do. No. You just know the next thing. And then you know the next thing. You don't know until you get there. Now what? Yes, right? Because do you guys see what I'm going to eventually want to do to get the T piece down? What am I eventually going to need to do? Take a log, take a natural log, right? So don't I want to get this 900 out of the way? Okay, so I'm going to divide the 900. So I get e to the negative 0.6t equals 1/9. And then what would you do? You kind of gave it away a minute ago. Yeah, take a natural log. What really kicks ass here about natural log, when you take the natural log of this side, yeah, so if I do the natural log of both sides, ln and e to a power, they cancel, right? They're inverses of each other. So let me see, I get negative 0.6t equals natural log of 1/9. And now, of course, the last thing I got to do to get t by itself is to
by negative 0.6.
yeah, divide. Oops. Divide by negative 0.6, divide by negative 0.6. So t equals this weird ass thing, and then you just have to be able to plug that in the calculator correctly. So I'll see if we can do that. I'll try to plug that in the calculator. Let's see what we get. Let's see what I said. Yeah, I think it's about 3.5. What is it? So natural log of 1/9 divided by negative 0.6. Dude, alright, not too bad. Are you guys able to do that? Of course, if you don't have a calculator, that's really, really difficult. What'd you get?
3.6?
Yeah, like 3.66? That's pretty close. 3.66 what? What units does it say time is in?
Years.
Years. So in a little over 3.5 years, the fish, there will be 900 fish. Now that's the model, correct? That's the model of the population. What could happen in those years that might make it not 900 fish? What could happen?
Disease, natural
Yeah.
disasters.
There you go. I love it. Disease could happen, natural disaster. Maybe more people come there and fish. Maybe nobody goes there and fishes, and the population grows faster, right? I like it. Okay. But this is the model, and if the model holds, then there will be 900 fish in a little over 3.5 years. I like it. So what's funny to me is, have you guys heard of like the population problem on the Earth? There was a lot of analyses done a while back with models that showed we were going to reach so many people, and we're actually below that. So everybody goes, oh, you math people don't know shit. Well, what happened after we made those models? Things changed, right? Disasters, disease, viruses, so forth, right? So of course, the model was made at a time when those things weren't there, so of course it's less, right? So there's one idea about a model versus what actually happens, and that's why we're constantly updating models as we get more information. Okay, maybe. Okay. Okay, so it's kind of nice when they give you the equation to work with, but then you have to actually know how to solve it. All right. Anything else from homework stuff? Okay, and everybody got an updated homework sheet, right? Oh, so I will say one more thing here about section 6.7. Well, I'll say two more things. One is notice what does it say about homework 6.7? Extra credit, holy shit. Yay. Yes. Oh. Sure. So it's awesome. So you got a head start on extra credit. I will say one more thing about section 6.7. 6.7 is all about models of real life using exponentials and logarithms. That's what 6.7 is all about. And one of the really, really basic ones is the idea of exponential growth. It's something like, I don't know if they use the same, they should use the same letters. What should I say? Here we go. Oh, they use A, yeah. Okay. The amount, that makes sense. That's fine, I will allow it. So in general, you can say the amount of something, because there's not always a population rate, yeah. So here, this A0 is the initial amount. So a classic problem for this would be, you put 100 bacteria on a petri dish, and then you walk away. 2 hours, you come back, and now there's 700 bacteria. You guys got it with me? Then you wonder, what's the growth rate for this bacteria, right? So real quick, let's just do the one I just said. So you put 100 bacterium, in a petri dish, not a peach tree dish, as some Congress people appear to believe. 100 bacteria in a petri dish, and then you go walk away for 2 hours. 2 hours later, there's 700 bacteria. How long until it overtakes the Earth? No, that's what I'm saying. Can anyone identify for me any piece of the equation and the value that we have for it? Is there anything in the equation that you just know from what I've told you? Like, does t equal 7? Does k equal 15? T equals 2. So apparently time is going to be in hours. So t equals 2. Okay, Jeff. What else? What else do we know? Say again? I'm sorry? B? What? B?
Oh.
Yeah, A naught. That's my initial amount, is 100. And then what's my final amount? 700. So what's the letter that I don't know? K. And K, not surprisingly, is related to the growth rate. So if I have a certain thing that I know its growth rate, if I know the growth rate, I can then predict how many of that thing will be there after so much time. So, go ahead.
K is the growth rate?
K is related to the growth rate, yeah. So watch this. So let's see. So now you just plug stuff in. This is a little bit easier than that last equation we did. So try to set it up and see how far you can solve this. It's really just like the last equation, just easier. Try to solve for k. I'm going to kind of catch up to you. Oh, Jesus. That's even worse. All right. So, what do I do first? Divide by 100. You gotta get the 100 out of the way because you want to attack the e with the natural log. The stupid 100's in the way. So move it. So we divide by 100. Get out of my way, stupid 100. All right. So now I get 7 equals e to the 2k. Of course, then I'm going to take natural log. Natural log of 7 equals, what do these do? Cancel each other. So I get k is natural log of 7 over 2. I think it's going to be roughly 1. Let's see. It's gonna be like, oh shit, 1.7. What is it? 0.97. 0.97? Is that what you guys got? Okay. And of course it goes 97, blah, 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 all right. So give me one more decimal, please. 2. And some 2, okay. Okay. So now watch. We got this k from observation, correct? I had some bacteria. It's like this new alien bacteria. We're up on the space shuttle, right? Or the space station, whatever. We got this new alien bacteria. We put it in the petri dish. We walk away. We come back. Now there's 700 of these bad little things. I'm like, all right. Now I know the growth rate. So now can I predict how many there will be after one day? How many after one day, which is of course 24 hours? How many will there be after 24 hours? Starting back at the beginning, right? So I don't know how many there's going to be, but I know there was 100 to start with. And now I know k is 0.972. And I know t is 24. So now I can just plug and shove. But this is a beautiful problem because we know the model it should follow. We observe something, and then we know more. And now I can make predictions. That's the whole power of mathematics. Now I can predict, if I wait a day from the first time I found this stuff, how much will there be, right? So be really careful when you put this in. All of this has got to be in the exponent. So let's see.
2 would be a 3.
2 is a 3. Oh, 973. Thank you. So I'm going to round that correctly. Is that right? Everybody else? I'm kind of outsourcing this. So let's see, what would this be? See if you can get this. Make sure all of that's in the exponent. Dude. Yeah. Let's see if you know how to interpret what you get. If you have a calculator. Did anybody get that yet?
1.385?
Be careful. No, it's not 1.38, whatever. It isn't. Right? 1.386? Can't be that. Doesn't make any sense. If I start with 100, I'm going to have 1 point something of them after a day? No. What's at the very end of that? What's at the very end of that number? If you look at the screen, what's at the very end? E12. Anybody remember what E12 means on the calculator? That's times 10 to the. So this is 1.386, roughly, times 10 to the 12th. So it's 1, 2, 3. I've moved the decimal 12 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to have this many bacteria after a day. Do you guys understand? That's a problem. That's a lot. Maybe? So let's see, what is this? 1,000, million, billion, trillion. 1.386 trillion. Almost as much as the deficit of the US. It's crazy. That's a lot. Maybe? Is that right? Yes? No? So this is what happens a lot in real life. We have models, we make observations, and then we can make predictions. That's exactly how weather works, or it doesn't. Why doesn't the weather prediction, why isn't it 100% accurate? Because there's so many variables involved. We don't have good enough models yet. We don't understand all of the variables and how they interact. Believe it or not. Are you guys with me? So we do the best we can. When we forecast where a hurricane's going to go, we actually use like 50 different models, and then we kind of average them. And that's how we predict where a hurricane's going to be. Kind of crazy. Okay, I'll stop. Okay. So that's all I'm going to say about that section. It's extra credit. So if you do it, and you do well enough on it, it'll just add to your homework score. So if you have 100 homework score, it'll be above 100, your homework score. If you didn't do some homework or whatever, it's going to cover some of that for you. Does that make sense? If you want to do the homework. You don't have to do 6, 7 at all. It's extra credit. Now we get to the real meat. This is kind of a huge day. How many of you guys have done trigonometry stuff before? I think I've asked you once before. How many of you guys have never done trig before? Anybody? Okay. And the rest of you, I don't know. You've both not done it and done it, so that's neat. Some of you guys didn't raise your hand at all. Okay. There's some basic things we have to start with before we get into the real trig. And one of the most basic things is just, what the hell is an angle? That's kind of a weird thing to try to describe. Can somebody tell me what an angle is?
The circular measurements between two lines point intersect.
Not in general. That's the specific possibility, right? Even then, it doesn't quite tell me what an angle is. So how do you draw an angle? I sort of just did it in the air. How do you draw it? Just go ahead and draw an angle. What do you have to use to draw an angle? Just tell me the most basic shit. What do you draw to make an angle? 2 ones. Not quite lines. Don't you draw, like here's an angle, correct? So now we got to go to really basic geometry. Now some of what we're going to talk about is not really going to come be a part of this, but you have to know what this is. Does anyone remember what this actually is? Something that has a definite starting point and goes off in one direction forever?
Segment.
Segment would be it doesn't go forever. So a line segment would be this. What's this? That's a ray. This is a ray. So a ray has a definite starting point and goes off forever in one direction. That's a ray. This is a segment. I like it. So if I give, so there's this point right here. What do you think we should call that point? What does that feel like it's related to things we've graphed before? Vertex. So that's exactly what so we call this the vertex. I'm going to give this the letter A. I'm going to call that B. I'm going to call this, that's right, E. Just pick it up. So this is just how many points are on this ray? How many points are on that ray? Don't say 2. How many points are on that ray? How many points are on that ray?
3.
Infinite. Every single point I go through as I draw it is a point on the ray. There's an infinite number of points on any line segment, so on any ray, there's definitely an infinity. All right, how important is that? Not terribly important. So what did I do? I just picked 2 of them on each ray, right? And I made sure one of them was the vertex. So that's a basic angle, correct? If I ask you to draw an angle, I would think most of you guys would do that. So you basically did it. Now we're just being more specific about what all the parts are. How would I reference this angle? What would this angle's name be? Let's call him Jeff? No. Using the points I identified. Does anyone remember how to reference that angle? This is angle what? BAE, 11. Or EAB. Or A. Cool, I like it. Those are all valid ways to identify that angle. All right, so nothing crazy, right? Some of this stuff is a little technical, but still it should be hopefully coming back to you. All right? So tell me this real quick. If I have this picture, and I want to identify this angle, how would I do that? Why can't I call it angle J? Why is that not good? I want to identify this angle. Why can't I call it angle J? What could angle J reference? Couldn't it reference this? Couldn't it reference this? Couldn't it reference this? You guys see what I'm saying? So why was I able to do it here? Because there's only one freaking angle there, right? Now how many angles do I have here? How many angles are here?
3.
Good! I love it. The little one, and the big one. Kick ass. So I can't just say angle J. It's not specific enough. It doesn't really identify which piece I'm talking about. So how do I identify just this? LJM or MJL, right? As long as J's in the middle. How are we doing so far? Is this all right? We're just talking about, I'm given some angle, how do I talk about it? So let's do this. What if it sat in a triangle? Say a triangle, oh jeebus, ABC. Triangle ABC. How would you reference this angle here? Give me 2 different ways.
ACB,
Say again? Oh, ACB, sure. Or?
BCA,
BCA? Okay, give me 3 ways. Or? C. Why can I do that now? Because there's only one angle coming off of C, correct? So if I say angle C, you all know what I'm talking about. Here, if I said angle J, what the shit am I talking about? There's 3 things that could be. Okay. So be really careful. If you try to use one letter for an angle, make sure there's only one possible thing it could be. If it's this situation, you can't call it angle J. It's not specific enough. Okay, nothing crazy yet. Blah, 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 blah. blah, 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 blah. Okay. So if I have an angle just sort of like hanging out in space, could you guys, for example, if I make this angle here, can you identify, can somebody guess how many degrees this is? Give me a guess. It's less than what? 90. It's a little less than 90, so what would you say? It's definitely not 45. It's a little bigger than 45, isn't it? Maybe? So I would say maybe I would take like 50 or 60 or something. Right? So it's like 50 degrees. So a little bit bigger than 45. 45 would be exactly half of 90. I guess. So a 90-degree angle, what do we also call it? Right angle. 45 would be half of that. So this is a little more than 45. I like it. So where the hell did these degrees come from? So how many degrees are there in a full circle? Why? Do you guys know why? Did it have to be 360? All right, I'm about to blow your mind. It didn't have to be 360. It could have been any freaking thing. We made that shit completely up. But we made up basically everything that we ever do. Didn't we make up all the letters that are making the words that I'm talking to you right now? Of course we did. But then we gave them meaning and we used them to do shit. The reason we picked 360 is twofold. One is because, can you divide 360 up in a lot of different ways? Can you divide it by 2? Can you divide it by 3? Can you divide it by 4? Yes. Can you divide it by 5? Ends in 0. Yes. Can you divide it by 6? Yes. Can you divide it by 7? No shit. All right. Well, that's all right. Right? But you can divide it in a lot of different ways. What else do we use that's based on like 60? Time, right? 60 seconds in a minute, 60 minutes in an hour, blah, 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 right? And we actually kind of stole that from the Babylonians. The Babylonians, real quick. Sorry, kids. Going on a little side journey. What's our number system based on? What number? 10. I don't know why it would be. Nobody knows. Nobody has a clue. Babylonians had a number system based on 60. Whoa. So when they wrote 1, 0, that actually meant 60. So we kind of stole the way we do time and circles and all, we stole it from the Babylonians. Okay, how are we doing so far? All that stuff was side note. It's not going to be on the test. Okay. So, again, this could have been any number. This is completely made up. We just chose it. There's a lot of different ways I can break a circle up, and we just decided to break it up into 360, what we call degrees. That's how we decided to break it up. Okay. Blah, 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 blah. Okay. So, it's going to come back to this. I kind of did that out of nowhere. And real quick, why does it make sense as 360? Well, if this is 90 and there's 4 of them, obviously that's 360. So we got a 90-degree angle. There's 4 of them inside of a circle, so 360 degrees total. Okay. Now, we're going to improve on this, by the way. Degrees suck. Degrees suck. They're not great. They're not good. But we're going to use degrees. Don't get worried. We're going to use degrees, but we're actually going to use something that's better also. And if you don't like it, too bad. We're going to use it. And they're called radians. Some of you guys know about radians. And some of you guys are like, I don't know what the hell that is. Okay, so we'll talk about it later. Right now, I just want to say one more thing about angles. If I have an angle just kind of sitting out here in space, this is angle A. That's not in what's called standard position. So standard position for an angle is this side here. Let me be specific. Say that's B and that's C. This side here needs to be on the x-axis. And then the other side will be this far away from it. Yeah. So that is now in standard position. I just rotated it so that the what we call the initial side sits on the x-axis. And this is what we call the terminal side. So if I were to move this side a little bit, what happens to the angle, of course? If I just took this side and moved it, the angle gets bigger. Yeah, the amount that it crosses over in a rotating motion gets more, gets bigger. Okay, maybe. So in a standard position just means put one of the sides on the x-axis. So if that's true, how would you draw something that is a 0-degree angle? Huh? So the vertex would be at the origin, right? So vertex at the origin. And then and then here's the initial side. And then if it's 0 degrees, how far away do I put the terminal side? It goes 0 degrees. It's just going to be on top of this one. So this would be a 0-degree angle, is just one that doesn't open. Then I can make it 10, 20, 30, 40, 50, up to 90, right? I can make it all those intermediate ones. Are you guys sort of with me? So normally, when I'm looking at like a circle, I see this as being the 0. So what is this? What angle measure? 90. What's this? 180. What's this? 270. And then, of course, what's another name for this? If I keep going, 360. And then I can keep going, so this will be 450. And I can keep going. Oh, okay. So that's the weird thing. In fact, what would this angle be? What's special about this angle if I go this way? Negative. So this could be negative 45 degrees. So if I move counterclockwise, it's positive. If I move clockwise, that's negative. So this is me telling somebody, so face 0 degrees. Now rotate negative 45. Oh, okay, right? So I'm just kind of orienting somebody. So if I say positive 45, they turn this way. If I say negative 45, they turn this way. So can somebody tell me another way to reference this angle that's not negative? The same angle here, what's another way to reference it? Another way to get here, basically. So if I told somebody to move negative 45, they'd end up facing this way. Can I tell them a positive direction to go, positive amount, so they end up facing the same way? 315. Right? What is 360 minus 45? 315 degrees. So negative 45 degrees is the same as 315 degrees. You end up in the same place. Is that cool? Okay, I like it. So, for example, let's do this right now. What's another name for, what do you got, Jeff? I'm going to kind of give this away a little bit. What's another name for 730 degrees? What's special about that one? How many rotations did I do? What's a full rotation? 360. So how many of those did I do plus a little more?
10% or 2.
I did 2 rotations. What would 2 rotations be? 1 rotation is 360. What's 2 rotations? 720. So how much past that did I go?
10.
So 730 degrees and 10 degrees are the same. If I told somebody, turn 730 degrees. Okay. Oh shit. Okay. Right? I could have just said turn 10 degrees and they would have been in exactly the same place. Yeah, I like it. I actually got a little dizzy. I'll be alright. Okay. It's not too bad. So what we call these two, let's see if this makes sense to you. We call these co-terminal angles. They both end co-terminal, terminate. Both, terminal, end. They both end in the same place. So how many different ways is there in general to identify this angle that we call 10 degrees? How many different ways is there to identify it? Could I rotate again? How would I figure out another way to identify it? What would I add to 730? You can do it. If I'm facing 10 degrees, I can rotate twice and now that's 730. Can't I just rotate again? Would I just keep adding 360? For how long? Forever if I wanted to? Can somebody give me a negative angle? That's the same as 10 degrees. Negative 350. If I want negative 360, where would I end up? If I want negative 360, I of course would end up back at 0 degrees. Is that cool? So if I go negative 350, don't I end up 10 degrees short? Yes? So if I go back negative 350 degrees, I end up at the same place 10 does. So how many negative representations of 10 degrees is there? Infinite number. I can just keep subtracting 360 forever. Are we ever going to do that? No, don't freak out. We're not going to make infinite lists. Don't worry. Maybe. All right, how's everybody doing so far? It's a little technical in some places, but this should be stuff you kind of know a little bit about at least already. Okay. Oh, let me keep myself straight. There's so many little pieces to this. Blah, 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 blah. Blah. Okay, we're there. Okay, good. Degrees suck. I like that. So, since degrees suck, let's talk about what's better. The reason degrees suck is because they're completely made up. They don't have any units. They don't mean anything physical, really. I want to create a way to identify how much something's rotated, and I want it to mean something physical. All right, this is way too cool. So you kind of go with me on this. This is way too cool. Okay. Any circle I draw, any circle in existence anywhere, has a radius, correct? Yes? You guys agree? Yeah. One radius. So we'll call this R. It's got a radius, yes? Right? Stay with me. This is so cool. You gotta stay with me. It's so freaking cool. Okay. No, you shut up and just do it. If I took the radius, imagine this is something I can actually hold. I'm gonna take the radius, and I got it right there in my hand. I got the radius. And I'm gonna do this to it. All right? Or I'm gonna get somebody else if I'm not strong. Could you do it? And then I'm gonna put it. Everybody with me? So I take this over here, and I bend it. And then I put it back on the circle. So this is this bent. So how far, if I walked this, how far would I go?
One radius.
One radius. Whatever the radius, if the radius is 7 meters, that would be 7 meters long, right? I don't know what the radius is, it's just the radius. So watch how this makes sense. How many radiuses, or radii to be specific, or correct, how many radii did I walk then? I walked one radius, right? So we call it a radian. So 1 radian is just how far you would make it if you walked 1 radius length across the circle. Let that make sense. That kicks degrees ass. Because now it's physical. That's physical. I can actually walk that length. So this is 1 radian. So this angle is 1 radian. That's much better than degrees. You guys might not agree for a while because you're not used to radians. Just like metric is much better than the shit we use. You guys won't agree because it's new. You don't know how metric works. Maybe some of you guys do. Okay. Are you guys with me so far? So watch. What if the circle had been smaller? Do you guys see how this still would go here? It would still end up at the same freaking place? Do you guys see that? That is still 1 radian. Because as my circle gets smaller, my radius gets smaller. And if I walk the radius around it, I still end up in the same angular place. Whatever this angle here is, which is 1 radian, it's exactly the same here. What if my circle had been bigger? I would have walked 1 radian and I would have made it right there. Maybe. So this is valid. 1 radian means the same angle amount. So does it make sense then that there has to be a connection between radians and degrees? Isn't this some amount of degrees? Of course it is. We just don't know what it is yet. So let's figure it out. So what I need help from you guys is, how many radians does it take to get all the way around, to get to the center of it, to get all the way around a circle? How many radians? And whenever I say how many radians, that means the number of radiuses, right, or radii, to get around. So what is that distance around? What is that called?
Diameter.
No, the distance across is diameter.
Circumference.
What's the distance around?
Circumference.
Circumference. And does anyone remember a formula for the circumference? Any formula for circumference?
Pi r squared.
Say again?
Pi r squared.
It's squared, so it's an area. Do you see? So that's the area of a circle is pi r squared.
2 pi r.
2 pi r. What's really funny is if you just take the square down, 2 pi r. Does that sound familiar to anybody? No? In fact, do you guys know where pi comes from? Not, I mean, pi. Do you guys know where that came from? Have I told you this already? If you take any circle, I'm pretty sure I said this to you guys. If you take any circle and measure the circumference, and then you measure the diameter, circumference divided by diameter is always the same number. And over history, every civilization has had a different approximation. I told you the Egyptians used 22 divided by 7. So what's 22 divided by 7, Riley, if you can do that, or anybody? Yeah.
3.14285.
All right, that's pretty close. What is pi? What's the value of pi? 3.141596, blah, 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 right? There are people that memorize the 50,000. I don't know what the hell the 7th place is, so don't worry. Be really careful. Pi is not 3.14, right? Even though if you write it in a funky way and read it backwards, it looks like the word pi. Do you guys see that? Have you guys never seen that? If you read it back, if you reflect it, it looks like the word pi. Okay, which is nice, which is neat. It's just a coincidence, right? Or is it? I don't know. So this is where we came up with the letter pi, because this divided by this was always the same number, no matter how big or small. And how does that lead to this? Well, if I multiply diameter up, I get here, correct? And then how does the diameter relate to the radius? It's twice as big. So this is twice the radius is the diameter. So that's where 2 pi r comes from. Maybe? Okay, all right. You guys are like, this is in history class. All right, I'm sorry. So, coming back to this. How many radii are there if they go all the way around? Well, how far is this? Isn't it 2 pi r? So how many radians? 2 pi of them. Does that make sense? What's the number of radii to go all the way around? 2 pi of them. So all the way around any circle is 2 pi radians. That is how to get all the way around any circle. Okay? So what would halfway be?
Pi.
Does that make sense? Yeah, that's pi, right? And how many degrees is halfway? 180 degrees. So 180 degrees is the same thing as pi radians. Those are the same thing. Just like 12 inches is the same thing as 12 inches. Same, 1 foot, right? Same way. I know you all knew that. You're just like, oh, this guy wants. So I can use it the same way to convert between the two. So if I know that I've got 45 degrees, how can I make that into radians? Here's a beautiful way to do it. What unit am I currently in? Degrees. And I don't want degrees. I want to make it radians, correct? So if I want degrees to cancel, would I put it up top or would I put it on the bottom? If I want degrees to cancel. Because I'm not sure. I'll put it down here. Wouldn't that cancel? So where would I put radians up top? And what did we just say? How many radians is how many degrees? How many radians is how many degrees? Pi radians is 100, so pi radians is 180 degrees. Can you reduce this for me? 5 goes into 45, well, let's do it this way. 9 goes into 45 how many times? 5. And the radian and the degrees cancel, right? And 9 goes into 180 how many times? 20. 5 goes into 20 how many times? So this is pi over 4 radians. Maybe? Let's see why this makes sense. Remind me, if I go all the way around, that of course is how many radians? 2? No? 2 pi radians. I love it. So radians, let me be careful. They don't always have pi in it, but they could. How much of the circle is this? What fraction of the circle is this? A quarter, right? Which is why we call that, it went right out of my head. Not quartiles, I'm thinking about statistics. Quadrants, there it is, Jesus, right? So this is why we call these quadrants, because you're split into 4. So this would be what? Wouldn't this be 1/4 of 2 pi? Is that cool? Do you guys see that? Isn't this 1/4 of the way all the way around? So it's 1/4 of the whole way around. 1/4 of 2 pi is pi over 2. So 90 degrees is the same thing as pi over 2. And what's 45 degrees compared to that? 45 degrees cuts 90 in half. What's half of pi over 2? What's half of a half? A quarter. So this must be pi over 4. So that jives with what we just figured out there. Okay, let me stop. By the way, let me just say this right now because I'm going to forget to write rad. If you see this, that means degrees, obviously, right? If you see this, and it's an angle, that means radians. We normally don't write rad. So if it doesn't have anything next to it, and it's an angle, radians. It's only degrees if it has an actual degree symbol. Are you guys with me? So if you see, like, draw an angle of 90, doesn't mean 90 degrees, it means 90 radians. Okay, So, let's do another example of this. Let's say I have, here's a nice one, here's a beautiful one. You ready? So going from degrees to radians, always a little bit weird. Going from radians to degrees is easy because what is pi? How many degrees would pi radians be? We just said it a minute ago. How many degrees is pi radians? 2 pi radians is all the way around. 180. So what can I replace pi with? 180 degrees. 6 goes into 180 30 times. 30 times 5? 150 degrees. So 5 pi over 6 radians is the same thing as 150 degrees. Where would 150 degrees be? Which quadrant is 150 degrees? What's this?
180.
180. So where's 150?
The second quadrant?
Yes. It'll be like 30 back from here, right? There's 150. So 5 pi over 6 is also right there because those are the same things. Why does that make sense? Why does that make sense? From here to here is how many radians? What's 180 also known as? How many radians? Pi. So if I don't quite make it to 180, shouldn't I have a little less than a full pi? A full pi was 180. So if I'm not quite at 180, I should be a little less than a full pi. Do you see how this is 1/6 less than a full pi? I come in and there's 5/6 of a pi left. I'm still happy because I managed to get there before it was all gone, right? And maybe.
What is a radian equal?
A radian is always the length of a radius. So that's why it scales with the circle. Right? That's why no matter how big a circle is, if the circle's like this, and I go 1 radius around, no matter how big it gets, and I'll go 1 radius around, I always end up at the same angle place. That's why I can identify angles with radians, because radians scale with the circle. So, again, for this circle, 1 radian would be roughly there. Like taking this and bending it. Is that cool?
Yeah.
So that's how long 1 radian, let's say this is 7 inches. How long is this then? Also 7 inches. The same thing, just curved. All right, so what if I have a bigger circle? And this radius here is actually 13 inches. And I go 1 radius. You see how I stop at the same place? If I take that and bend it, I stop at the same angle place, right? But how long is this piece now? 13 inches. Well, what's the angle measure for both of these? 1 radian. Because how far did I actually physically move in each case? I want 1 radius length. So that's why a radian, it means different things in terms of actual distance you travel. It means 1 radius. So if I have a big ass circle, 1 radian actually takes me a while to go. But what size angle do I rotate through? Exactly the same. Okay, I was about to. Do you guys remember merry-go-rounds? Everybody remember? You ever been on a merry-go-round? Merry-go-round? No, what's the name of the, not the merry-go-round, but the what do you? No. The ones where you had the bars on them and they were circular. And you have the bars on them. So you can hang on and somebody can twist it around. It's not really merry-go-round, but you guys understand what I'm saying? Maybe? If you're standing out here, you go further than somebody standing closer to the center. But you go through the same angle. You sweep the same angle. Do you guys get that? Okay, maybe not. Okay. So again, if I go 1 radius on this big dude, versus 1 radius on the small dude, don't I end up going through the same angle? So watch this. Okay, let's say that's 30 degrees. Is that cool? That's 30 degrees, right? In fact, let me give this some more space. Okay, go away. So let's say this is 30 degrees. Right there, that's 30 degrees, right? What if I extend this? What is it now? If I just keep going in the same direction on both of these, just keep extending this. What is it now? 30 freaking degrees. Of course, the angle doesn't give a shit how long the sides of it are. 30 degrees, real quick, see if you guys agree with me, is also pi over 6 radians. Can you guys see that? What's pi again? How many degrees is pi? 180. What's 180 divided by 6? 30. So this is pi over 6. No matter how far that goes, that's pi over 6. Yes?
So once you get to over 180 degrees, do you have to use 12 instead of 6? Or?
Oh, no. Okay. All right. That's an interesting question. So I just erased it. The problem we just did a second ago, that was 5 pi over 6. Remember that?
Yeah.
Okay. And remember how that was 150?
Yeah.
Why does that make sense? Because here's pi. How much is 30 degrees? Isn't 30 degrees pi over 6? You guys with me? How far back is this in degrees? This angle right here, what is it? You guys see that? 30. That's 180. That's 150. So how far is this angle? 30 degrees. Right? How much less than a full pi is 5 pi over 6? If you had a full pi, how much would you have to eat of it so that there was 5/6 of it left? 1/6 of it, right? So pi over 6. So that is, I really want you guys to see, isn't this also pi over 6? It's pi over 6 back from pi. It's 1/6 less than a full pi. Okay, so continuing on. If I were to go 30 degrees this way, what angle, what degree measure would I be at now? If I go 30 degrees past this, 210. But I am also pi over 6 past pi. I'm 1/6 more than a pi. I've gone 30 more degrees, and 30 degrees is pi over 6. So what is a full pi plus pi over 6? Don't overthink it. How many sixths is a full pi? How many sixths is a full pi? 6. It's 6/6, right? If I had a full pie, if you cut it in 6 pieces, how many pieces are there? 6. How big is each piece? 1/6. So if that's 6/6 plus pi over 6, what do you get? 6 pi over 6 plus pi over 6 is? 6 pi over 6 plus 1 pi over 6 is? 6 pi plus pi. 6 pi plus pi. 7 pi. If I have 6 pi and you have a pi, together we have 7 pi's, right? So it's just like terms, like always. I don't care if it's 6x plus x. I don't care if it's 6y plus y. I don't care if it's 6 pi plus pi. 7 pi. So this is 1/6 more. This is 1/6 less. So you don't have to go to pi over 12 to go further, yeah.
Okay.
Yeah.
So
Oh, go ahead.
if you're doing like 360 degrees, it's 12 over 6.
Yes. Sort of. I don't know, sure where you got that, but basically 12 pi over 6 is 2 pi.
Yeah.
Okay. Now I could do, what would pi over 12 radians be? How many degrees would that be? How do you do that? Pi is how many degrees again? 180. Pi radians is 180 degrees. That kicks so much ass. So now you just have to make pi. What is pi? 180 degrees. And what's 180 divided by 12? How long does it take the Earth to rotate once? The Earth rotate. How long does it take?
365 days.
No, not the Earth go around the sun. The Earth itself
24 hours.
rotate 24 hours. Thank you. That's a day, right? So it takes it 24 hours to rotate how many degrees?
360.
360, a full rotation. Are you guys with me? What is 360 divided by 24? 15. I don't know if you know this, but there are people out there that think the Earth is flat. Still, right? I'm not talking about back in the 1600s. I'm talking about today. And if any of you believe that, keep it to your damn self, right? Continue coming to college. It's where you need to be, right? If you feel offended, oh my God, Earth ain't damn flat. So there is a piece of equipment that measures, it's like a gyroscopic. It measures the rotation of something. So there's one group of flat earthers got a hold of it. They thought this would prove the flat earth. They would prove it is zero. They thought it was going to show no motion. But over the course of 24 hours, it measured a 15 degree per hour drift. Because over the course of 1 hour, the earth moves 15 degrees. Do you guys kind of follow what I'm saying? So this has nothing to do with the ideas here. It's just a real world application of this stuff. Okay, you got the earth right here. Rotate. Okay. So let's do something just kind of like by itself. Can you convert? Don't say anything. Can you convert? What do you got? You 60 degrees into radians. Don't say anything. Just do it. Convert 60 degrees into radians. Man, I've got to get some numbers. So on the bottom you have to put degrees so they cancel. And on the top you're going to put radians. How many what's in what here? How many degrees are in how many radians? What do we know? 180 in how many radians? Pi. You. That's it. What's 60 divided by 180? 0 cancels, so it's 6 divided by 18. 6 goes into 18 how many times? 3. So you get pi over 3 radians. 60 degrees is also pi over 3 radians. You can see that pretty quickly. Isn't 1/3 of 180 60? So 1/3 of 180 is 60. Bam. You don't have to do this all the time. Some of them you should be able to kind of like tell what it's going to be. So at some point in the future of this class, I'm going to say stuff like pi over 4. You immediately will know that means 45 degrees. Yes? For example, and pi over 3 means 60. Yeah?
To cancel degrees, you want to do 180? You want to divide it by 180?
We did.
Okay.
What's 60 divided by 180? 1/3.
Is that like a general rule?
Yes. Just like 12 inches in a foot, there are 180 degrees in pi radians. So I can convert things the same way we convert. In fact, real quick, guys. If I had 76 inches of material, how many feet is that? What unit do I not want anymore? Inches, right? I mean, some of you guys should know. What do you do with 12? You know it's going to be 12. But do I multiply by 12? Do I divide by 12? If 12 inches is 1 foot, 24 inches is? If 12 inches is 1 foot, 24 inches is, I can almost hear you. 2 feet, right? Yes, 12 is 1, so 24 is 2, right? So don't I divide by 12 to see how many feet it is? So that's what, if I want to get rid of inches, I would put it here. See how they cancel? And I want to go to feet. So there's 1 foot in 12 inches. 76 divided by 12 is roughly 6 point,
3.33.
oh yeah, 3 5. 6 1/3 feet. So do you see how this is really the same idea? Just like we know 12 inches in a foot, we now know 180 degrees in pi radians. Same way. Why is it so much easier to go the other way? So what if I said 11 pi over 12? That's easier. Why? Well, if I said 5 feet, how many inches is that? What can I replace feet with? 5 feet. That means 5 times, every foot is how long? 12 inches. So 5 feet is 5 times 12 inches, because a foot is 12 inches. Well, what is pi? Radians. How many degrees is it? 180. So I just replace it. 11 times 180 over 12. Which I believe is 165. Is that right? I'm pretty sure that's it. Okay. So if I ask you right now, can anybody tell me what is a radian? What is a radian? Huh? No, pi radians is 180 degrees. So don't want a number. I want you to tell me what a radian is.
The distance along the circumference you would walk if you tried to walk the distance of a radius?
Yes, it's just a radius along the circle, right? If you walk a radius length, that's the angle you go through. That's the radian. 1 radian is the angle you make if you walk 1 radius along the circle. That's the angle you make. That's what a radian is. That's why it's better than degrees. Why is it better than degrees? Because it's a physical measurement. We just made up 360 degrees. We just made that shit. It could have been 400. It could have been 3 degrees in a circle. It could have been. If the people that created it were, insane, they would have done that. And we would be talking about 3 degrees. And oh my God, that would suck so bad. Thank God I didn't choose that. Okay. All right. Maybe. Okay. No. Yeah, cool. So tell me this. What's the distance all the way around the circle again? The distance. Be careful. Two pi r. Okay, right? That's the circumference. Okay. So then I might say, okay. What if I'm here and this angle is pi over 4? How long is this? I want to know this length. So the length around the whole damn thing is 2 pi r. What would this length be? Well, I ask you this. How much of the circle is that? So this would be how much of the circle? How much of the circle would this be? Like 1/5, 1/8, 1/12, 1/3? How much of the circle would this be? This piece, it would be 1/4 of the circle, correct? So how much of the circle is this?
Right.
How much is, 1/8. Is that cool? It's half of 1/4, so it's 1/8. So wouldn't this be 1/8 of this? You guys see that? If the whole thing takes me 2 pi over r to walk around it, 1/8 of it should be 1/8 of 2 pi r. Well, what is 1/8? Oh God. Okay. Somebody work. What is 1/8 of 2 pi r? Help me out. Reduce it.
1/4 pi.
Pi over 4 times r. That's interesting. Remind me how many radians in the whole thing around? All the way around is how many radians? 2 pi radians, yes? Do you see how it's the angle measured times r? The angle measured times r. So if I call any arc length s, we're going to call arc length s. Why? Because the letter s does not show up in the words arc or length. So I'm sorry, in sometime in history, we decided s is arc length. This is equal to r times the angle that we go through. Come in r. One thing about this angle, which measurement is physically true, degrees or radians? Which measurement has actual physical properties, degrees or radians? Which one's better? Which one that I say is better? And someday you'll actually agree with me. Degrees or radians? Radians are better because they're physical. You can actually walk a radian. You can't walk a degree. You have to know more to be able to figure out what the hell does that even mean. So this angle has to be in radians. So let me ask you a couple questions. That's a formula that you must now memorize, but just let it make sense. So if I have a circle of radius 11 inches, and I walk along the circle's edge pi over 6 radians. What's the arc length that I traveled? How far did I actually go? Do you have a formula for that? Do you? Do you have a formula for that? Right there, yes. Yes, there's a formula for arc length. Right, so arc length is radius times angle in radians. Do I know the radius? What's the radius? What's happening? What's the radius? 11, right? What's going on? You guys all right? You guys just didn't want to say it because it's right there. You're like, dude, I can see it. Just put it down. So the radius is 11. And what's the angle? 5 or 6. So hopefully somebody's got their calculator. You guys all know where your pi button is on the calculator. Pi button on the TI is above your to the button, like your power button. So can you take a minute and figure out what 11 times 5 or 6 is? I think it's roughly 6. 5.75. 759, so it's 5.76 roughly. I'll tell you where around, by the way. 5.76 what? Inches. Okay. So if I walk along the edge of this 11-inch radius circle, if I go this many, so visually, I got a circle that's 11 inches in radius. If I walk pi over 6 radians, how far did I actually go? 5.76 inches. Why does that make sense? If I want a full radian, how far would I go? Let's see if everybody remembers. If I want one full radian, how far would I go? What's a radian mean again? The length of the, no, it means 180 degrees. What's just a radian mean? It's how long why do we call it radian? Because it's how long a radius is, right? So if I want one radian, how far would I go? How long is the radius? 11 inches. A radian is the radius curve. So one radian has the same length as the radius. That's why we call it a radian. It's a number of radiuses, right? So we just decided to call it radian, just to make it easier to say. Did we go a full radian? No. We went like pi, isn't this roughly a half? Is that cool? Isn't pi like really roughly 3? So isn't this like half a radian? So we basically went half of this, a little more than half of this. So what's a little more than half of 11? 5.76. It makes sense. We didn't go a full radian, so I didn't go a full radius worth. That's why we went less than 11. We went almost half of, or a little more than half of 11. Maybe. So one radian is just taking a radius, bending it, and putting it on the circle. So if I ask you if I'll go 1 radian, and you know the radius is 11, how far do you go if you go 1 radian? 11 inches. Because that's how far a radius would take you. Okay, maybe.
Is that curved angle?
Say again?
Is that curved angle on the circle 5.76?
No, okay. The angle is pi over 6 radians. The distance I would travel is 5.76 inches. All right, just to make sure you really see how this works. If I have the same circle, remind me if I have the same circle, how many radians is all the way around? Radians. Sorry, you might have said it. 2 pi. 2 pi radians. Is that cool? 2 pi radians all the way around. If I walk all the way around, how far would I go? Don't make too much of this. That's the what of the circle. You make it into a night, so it's now circumference, right? So all the way around circle circumference. What would that, if I walk around the circle, how far did I actually travel? 2 pi times 11. Right? So roughly 69, 70 inches? I don't know what that is.
69.115
That's pretty good. 0.11 blah 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 inches. Okay. Alright, so radians are just like degrees. They both tell you how far some angle has rotated. They're about rotation. They are related to the actual distance you would walk if you did that rotation along the circle. Does that make sense? So they're not equal to each other. They're related to each other. In fact, do we have a formula now that tells me how they're related? Yeah. So this is the angle measure that I turn through as I walk. And if I multiply that by the radius, I get how far I actually walk. I like it. Let's see. Nothing in here. Shoot. That's too bad. There's no meter sticks or anything. Damn. All right. Well, that's okay. That's kind of. I want something. All right, here. Alright. So watch this. So I'm gonna rotate this thing. Did every single piece of this go through the same angle? Yeah. You guys agree? Every single piece of this went through the same angle. Did they all go the same distance?
No.
Okay. All right. Is this sorry? Okay. All right. So I've got this right. So if I rotate it, didn't this cap go much further than this cap?
Yes.
But they went through the same angle. Yes? You guys get that? So the angle is not equal to the distance traveled. The angle is related to the distance traveled. Now, why would this go further, this green cap go further than this red cap? Because it's further out. Isn't the radius to this bigger than the radius to this? So that's why it makes sense that the relationship between how far I actually move versus the angle I rotate through would involve the radius. Because the further I am away, the more I end up actually traveling, right? So when we go around the sun and we go 15 degrees over, and Pluto, poor little Pluto, no longer a planet, but Pluto goes 15 degrees, Pluto's going much farther because it's much further away. So here we are, here's the sun, here's us, here's Pluto, right? So when we turn this much, Pluto turns the same amount, but how far does it actually travel? How far does it actually travel? Much further. That's why it takes so freaking long for it to get all the way around. How about Mercury? Mercury is like, I don't know. It doesn't take as long because it doesn't have to go as far. Maybe. So you got a difference between how quickly you move through an angle versus how fast you're actually moving. So if I rotate this, which piece of this is moving the fastest? Which piece of this has to go through the most distance? Aren't they all moving the same kind of angular speed? So it's right here at 0 degrees, right? And then 1 second later, it's at 90 degrees. Which piece went the farthest? The green went the farthest, correct? You guys all agree with me? Green went the farthest. Of course it did. So who's moving the fastest? If they all made it here in 1 second, but this guy went much further, who's moving fastest? This thing. Green is moving fastest. All right. So if in 1 hour you went 80 miles and somebody else went 350 miles, who's going faster? If 1 hour you went 80 miles, in 1 hour somebody went 350 miles, who's going faster? Guy who got 350 miles, he's going faster. He made it further in an hour, correct? Okay. All right, because that's the next level of this. Let me see if I can sneak this in. We'll do one more thing. So tell me this. Do you guys know the relationship between distance, rate, and time? Right? If you're traveling 80 miles an hour and you travel for 3 hours, how far would you go? So if you're going 80 miles an hour and you travel for 3 hours, how far do you go? 80 miles per hour, and you go for 3 hours. How far do you make it? Okay, if you're going 80 miles per hour and you travel for 1 hour, how far do you make it? 80 miles, because you're 80 miles per hour. 80 miles an hour for 3 hours. 240. So what's the formula you just used? You just did the speed you're going, the rate of travel, times time is your distance. Dirt, that's awesome, right? D equals RT, dirt. So let's use letters that are more related to what we're talking about. So if I'm moving in a circular fashion, I am moving in a circular fashion. I'm going around a racetrack, and going around a racetrack, it's not only circular, it's more elliptical, but I'm on a planet going around the sun, I'm an electron kind of orbiting the nucleus, right? Anything that goes in a circular fashion, the distance it's going is actually S, yes? So I'm going to replace this with S. This is velocity, is that cool? I'm going to just put a V there, times time. So velocity is that divided by time. Why does that make sense? Because what units do we use for velocity? What units do we use for speed? How fast did you go to get here this morning?
Miles per hour.
Miles per hour. Miles per hour. Right? So if you know the units on something, you can very often remember the formula for it. Okay. What did we say S was just a minute ago? What's the formula for S in terms of theta and R? What formula did we just do? S is equal to what? We just did this formula.
On theta.
R theta. Thank you. All right, let me introduce one new thing. So I'm going to put all this stuff together. I want to introduce one more thing. What do you think angular speed is? So linear speed is how far I go, what's the length I go over amount of time. So what do you think angular speed would be?
Is that like if you were like launching a projectile or something?
Not really. That would still be linear speed. This is if I have something spinning and then something else spinning. Which one has a higher angular speed? This one, obviously, right? Because it's going through so many radians per hour more, right? Faster. So linear speed is how many miles an hour do you travel? Angular speed is how many degrees or radians do you go per hour, right? So angular speed is the angle you go through divided by time, whereas linear speed is the distance you go through divided by time. Kind of makes sense. Angular speed should be how much is the angle changing over time. So angular speed of a clock, pretty slow, right? Especially when I talk about the hour hand, right? The minute hand, what's the angular speed of the minute hand? It would be one rotation every 60 seconds, right? Is that cool? Maybe. Did I say minute hand? I meant second hand. You guys doing all right so far? So how long does it take to go through the whole thing? That would be one rotation, or 2 pi radians per minute, right? That would be what the second hand does. The symbol we use for angular speed, you're going to love it. It's a very curvy W. It's actually the Greek letter omega. But if you call it W, I will understand. If you make it a W, I will understand. But it's supposed to be curvy, very curvy, right? It's like a little butt. So let's put all this stuff together. Watch this. What is S? What is S?
Radian.
R theta, right? That's what S is. What is theta divided by time? Omega. So, watch this. So velocity, how quickly my position changes over time is equal to the radius of the circle I'm traveling along times my angular speed. I really want this to make sense. So if I'm on the edge of something rotating, I'm going through certain angles over time. Well, how quickly am I just moving? How quickly am I just moving would be that angular velocity times the radius. And again, why does that make sense? Because when I had this big ass dude, the end of it was going the fastest. Why? Because it was the furthest out. Okay, so if I have something, let's see. Let's say that omega is what do you got, John? Let's just say pi over 2 radians per hour. That's omega. So it's an angle per time. Is that cool? So pi over 2 radians per hour. And the radius of the circle I'm traveling on is 80 feet. What is my velocity? What's the formula say to do? B equals RW, right, R omega. So what would you do? Yeah, 80 times pi over 2. So you get 40 pi. What's the units going to be? Here's where you got to be careful. What's weird about these guys is it means the number of radii. So it actually just sort of gets out of the way. So this will be per hour times feet. So it's feet per hour. And then, of course, if you tell me you're going 40 pi feet per hour, I'm going to stare at you blankly. I'm like, what the hell are you? So what is that if you multiply it out? 125, 124.57. I don't know, just making sure. Hey, what is it? Sorry? 125.66? Maybe like that? Feet per hour. Okay. So if you're rotating pi over 2 radians per hour, so on this circle, it takes you an hour to get here. Does that make sense? So that's what that means. Pi over 2 radians. So here's pi over 2 radians. It takes you an hour to get there. And it's 80-foot radius. So how fast are you actually moving through this distance? 125.66 feet per hour. Okay. All right. Let me see. I think that's obviously that's enough because that's the end of the class. All right. So that's section 7.1. So we're going to get further, obviously, into trigonometry next time.